Do you see the slides and
Yes,
also in presentation mode?
yes,
Okay.
yes. So we do see it.
I think I have to go back to them. They'll probably not see. Well, let's see if I can
We see
shift the
your
slide.
okay. We see your laser pointer clearly.
Okay, good. I was just wondering if I can shift the slides, but I will see. So thanks a lot for organizing this great conferences. I'm sorry that I cannot attend all the talks, but I will for sure look back on them because they are recorded. And I think it's a great idea to still have online conferences, even though we seem to be back. Yeah, because it's really like a inclusive way of also approaching people who cannot still not travel, and it's also, of course, a money issue. And today I want to tell you what we do in the terms of enzymatic synthesis of polymers. And I want to focus on furan-based polymers, but in the beginning of my talk, I also want to tell you a bit more why we should maybe be interested in that, and what other systems we do. I cannot show you all our systems, but if you are interested, you can always contact me later. And yeah, the reason why we are doing this is shown on this very terrible picture. Um, we have too much plastic waste, and enzymatic polymerization is not the only solution for this problem. But with our research, we are trying to tackle some of the problems that we have in the plastic waste. And in the beginning, we were always just synthesizing polymers, but now we are also looking more and more into also enzymatic degradation, into more green solvents. And also there, I don't have time to show you all of that. But I'm convinced that enzymes can be part of the solution, but of course, like anything, it's not the solution for everything. And I want to start like a longer talk always with some of the solutions we have for this problem of plastic waste and plastic pollution. And they are, of course, also not the complete solution. So you know that the European Union was reducing and banning the single use of plastic. So this is more or less plastic straws and this packaging. And if you're take some takeout, you no longer get the plastic spoons, but it's some wood composite, which is probably also contains plastic. So this is one way, but not the whole way, of course. But it's a good incentive because much of the plastic waste that is in the ocean and in our woods is actually from us. That's stuff that we maybe lose or on purpose just throw into the nature. And if we have less of that stuff, that of course helps. But there are also issues, of course, of food safety. There are people who cannot eat or drink because they have some sort of handicap, so they need plastic straws. So there's also another side to that story. And it is, like I said, not the complete solution. Then, of course, we have the circular economy approach. And this is, of course, very important. 30 years, 20 years ago, maybe even 10 years ago, we really made the polymers and we used them, and they were either disposed or burnt. And if you still burn them, you at least recover energy. But of course, you put a lot of energy and catalysts and all the way to the fine chemicals, to the monomers, into the polymers. And if you just burn them, yeah, you basically downcycle tremendously. So I have to put this panel away. So if you go to the circular economy, you really try to reuse the material, in our case, the soft matter plastics, on the same level that you have. I think you all know that the PET plastic bottles that we use for water, like this one, if you just shred them and extrude them, you cannot make a plastic bottle anymore. So it's downcycled to fibers for clothing. And clothing is, of course, still something that we wear and we use. But we should also look into recycling waste, mechanical recycling waste, that we keep the molecular weight of this PET intact, and maybe you can make plastic bottles from recycled plastic bottles. But in principle, it's important to keep as much carbon as we have in the soft matter polymer field into this loop. And there are people who calculated how much we can actually close this loop. And they are predicting that probably we lose 20 to 25%. So we cannot close this loop completely. But this would be, of course, a tremendous win if we come to this like 85% recycling of the carbon all the time. And personally, I really think that when we reach to that, and I think the goals are for different countries between 2035 and 2050, if we can really get to 85% of this recycling of the carbon, we won the game, because this 20% or 25% that we have to feed into the circle, that's still a lot of material, but it's not that we have to have megatons of polymers to produce in a pristine manner, and also the oil and the gas that we need from fossil resources will be a lot less. And I personally think in 2050, people will not talk about bio-based or fossil-based anymore, because most of the carbon we reuse, and the 20% we feed in is so little that that people will not worry about it anymore. This is actually a dream scenario, but I still have hope in that. And a good thing are also biodegradable polymers. I mean, we just saw a very nice talk about biodegradable polymers for medical applications. So if they come in our body, that they release a drug and then they degrade, and they are not toxic and never toxic for us. But in terms of commodity plastics, biodegradability is a good thing or a bad thing. And the European Union was just releasing a couple of months ago the SAPIA report on biodegradability of plastics. And I was part of this expert team who was writing on this report. And before, I always thought, oh, biodegradability, that's the thing that we should aim for. But then when talking to all the other experts, I really realized that it's good for applications that we cannot get back. Let's say the farmers, for instance, who put the plastic on the fields in spring, so that, for instance, the asparagus and the strawberries grow, and they cannot take the plastic films back, and then it has to be biodegraded. But also there's a societal challenge to that. So if we buy a plastic bottle and everybody tells you that it's biodegradable, people will again just throw the plastic bottle into the woods or the ocean. And biodegradability is time dependent, which we also saw in the previous talk. And it simply means that there's still too much microplastics in the environment. So biodegradability is also great, but we should also just limit it to plastics that reach the environment and also stay there, and that we cannot recover. And there's the bio-based polymers, and I was already commenting here on the circular. At the moment, we are still using too much oil and gas, and I don't know if you know where Groningen is. It's in the north of the Netherlands, so that's where I am right now, where my university is, and we have major issues with earthquakes because of we have a natural gas bubble under the ground. At the moment, there's again a lot of gas taken out. Because there's too little gas because of the war. And we have major earthquakes because of this. And of course, the gas is needed to heat, but also for fine chemicals, for monomers. So bio-based polymers is playing into this problem. But again, I really hope in the future we don't have to talk about petrol or bio-based anymore, because we can really have a circular economy. So these are 4 solutions of the problem of plastic solution that we have. There are many more, and there's not a single solution. And that's, of course, the problem that we have as polymer scientists in general. We somehow, and I'm pretty sure all of you who are in the field, when you are talking to your family or you are on a party, everybody says you're part of the problem, but we are, of course, part of the solution as well. But we also have to be very open about the limitations of all these approaches, and that they are just working together, and that we are also not there yet, because also I don't have time to talk to you about recycling, but also the recycling solutions, chemical recycling versus mechanical recycling, and also all the discussions around that, for which polymer it is the best. There still have to be many discussions to come. Well, I hope once to a solution. So coming to our research, we already started a long time ago with enzymatic polymerization. So we want to replace the metal catalysts, and very often very high temperatures used to synthesize mainly all polymers in industry, by enzymatic approaches. So in the beginning, we were trying to replace these catalysts, which can be toxic. Not all of them are toxic, by enzymes, lower the energy needed for that, lower the vacuum needed for the synthesis. And lately, but that's also already nearly 10 years, we also try to avoid fossil-based monomers and go to biomass-derived monomers. And what's not in this scheme, which I can touch upon just at the end of the talk, so we are also trying to do more in green solvents, that we, for instance, use ionic liquids or deprotectic solvents for our polymerizations. And the reasons why we use enzymatic polymerization is because enzymes are really efficient catalysts. I mean, for I think all of us, or most of us, it's at the moment the morning, so we had breakfast, and we need these enzymes to digest the breakfast, or even just the coffee. Everything in our body is done by enzymes, and they're very efficient, because otherwise life wouldn't be possible. And they are environmental friendly, and we can use them to catalyze reactions that otherwise we would need a lot higher temperatures, or more vacuum, or anything that's related to high energies. They act under mild conditions. That's more or less plays into the environmental friendliness. That can also be a problem, because if you want to polymerize in bulk, the monomers need to be molten, and some monomers just melt at like 200 degrees, and enzymes don't survive that. So then you basically also have to look for other solutions, either a solvent, but of course you will never synthesize commodity plastic on large scale in solution, and then maybe with greener solvents you could play into that, and they are compatible to each other. So that's also what's happening in our body. There's not just one enzyme which digests our food, but many, and it's a cascade. And we can also do cascades in the test tube with these enzymes to make polymers. And they are not bound to their natural role. You have a whole spectrum of reactions. If you compare your organic chemistry textbook with the biochemistry textbook, you can find the same reactions, and you can find an enzyme for this reaction, and then you can of course also make polymers with these reactions. And enzymes are selective. You have chemo, regio, and enantio selectivity. In commodity plastics, you don't really need that, but you could think of, again, the previous talk was about biomedical polymers, and there it might be important that you have a certain toxicity or a certain enantio selectivity of your polymer, and then you can also use enzymes for that. And if you're interested in this topic, there's just one textbook out there. So we did this like it's now 10 years ago, but it's still the only really entry-level textbook. But I'm sure your university doesn't have it online, or maybe not even in the library. And it's not a very cheap book. So about 1 year ago, our colleagues from Japan, Shiro Kobayashi, Oyama, and Kadokawa, they wrote such a Springer compendium, and I think all of you that work at the university, you probably have access to the online text. And together with Nico Poons, also last year, I edited a methods collection. If you really want to go to the lab, you can look up that one, which you probably also have online. And there you really have the recipes if you want to start with this topic. And yeah, you can also look into the original literature, but the field is still not that big, so there are not many groups working in that field. So this might be the cheapest and easiest approachable text at the moment to really start. And we have still in biochemistry 6 enzyme classes. If you follow like the biochemistry, they're of course breaking this up a bit and subdivide these enzyme classes. But for us, let's keep it with these traditional ones. And we mainly use oxidoreductases, transferases, and hydrolases to make polymers. And you can, for instance, even make conducting polymers like polyanilines, but you can do plexiglass with peroxidases or laccases. You can make polysaccharides or polyesters, and yeah, polycarbonates you can synthesize. And there are reports out there. But again, it's not that there are many people working in this field, and especially for the young people that might be listening, it's a very interesting field. It's a lot of synthesis, a lot of characterization. It's very interesting. So if you look for a new research field, it's definitely fun to do, and you can make new polymers, and you can make old polymers in another way, and it's very rewarding. And I told you that I want to talk about furan-based polymers. So these are mainly polyester polyamides. So let's look first into some of the things that were reported before by us or by others. And we mainly use lipases, or these are the hydrolase chemistry to do these reactions. And these enzymes usually hydrolase the ester bonds and triglycerides. And that's, yeah, if you had breakfast, I hope you had something also with fat for the vitamins to absorb. And in our body, also the lipases digest the fat by cleaving the ester bonds. And in the whole field of biotechnology, we of course don't use enzymes from humans or from animals. We use extremophiles. And the working horse enzyme in the field of polymerization, but also organic synthesis, is this Candida antarctica lipase B. It's coming from not from the Antarctic, but from close to Sardinia. It was found in an extremophile, and many people are using that. We are also using that. We are also using a lot of other enzymes, but I want to introduce you to this one. And we usually use it immobilized, and the commercial formulation is it's just Physisopt on a bead. It's an acyryl bead from Lanxess. So you get that commercial from Novozyme. You can also just do that yourself. I mean, it's really just shaking the enzyme suspension with these beads, and there are many ways to immobilize enzymes, and that's also a very interesting research field, because it's not well understood why immobilized enzymes work so much better and are so much protected against, for instance, your monomers. And yeah, we worked in this field of enzyme immobilization for a while. Yeah, but then yeah, you know how research goes. Then you diffuse away, or you don't find follow-up money. But I still find it an extremely interesting research field, and I follow the literature, and it's really amazing what other people find in terms of stabilization of enzymes just by attaching it to a surface or putting it into a pore, and then all of a sudden it's 100 times more active and survives 150 degrees in toluene. So there's a lot to gain also in this research field. But I wanted to tell you something about polymer synthesis and about polyester synthesis. That's a field started in the 1980s by Shiro Kobayashi and Richard Cross, so from Japan and the United States. And you can do a normal polycondensations. And you can also, of course, also do ring opening polymerizations. And if you see this, this N can be equal to 15, and that's a humongous lactone ring, of course. And this has no more ring strain, and you would have big problems doing a ring opening polymerization of this huge lactone ring. But the enzyme, of course, doesn't care. It realizes this ester bond and it cleaves it. And if you push the equilibrium to this side, then you form high molecular weight polyesters, which are an intermediate, because this N is again 15. They are intermediates between polyester and polyethylene, and have quite interesting properties. That's work from my colleagues from the Technical University of Eindhoven in the south of the Netherlands. It's also, of course, a textbook example of why enzymatic polymerizations can be interesting, because it's something that you cannot do easily with other synthesis approaches. And I want to show you shortly the mechanism of all these hydrolases, because we come back to that later also when we discuss results. So they are also called serine hydrolases because in the active site, the active amino acid, which is most important, is a serine. In our case, this is the structure of the CAL-B, the Candida arctica lipase B. We know that the serine is the amino acid 105 in the whole sequence. And this is, of course, not the whole enzyme. The enzyme is a big amino acid globular thing. This is an extreme zoom in the active site. You will see that this histidine is very important because it accepts hydrogen. And we also know that we have different groups which stabilize transition states. So if you now want to synthesize a polyester and you use an hydroxy acid, so here you have the hydroxy group, here you have the acid group. And if it's going well, then the acid group goes down first. And then you form a transition state, and you saw that the histidine abstracted the proton. And if it goes into the right direction that you want, you form a covalent bond. And if you come down with your second monomer, then it goes down with the alcohol group. You form again a transition state and a covalent bond, which is released. And then the whole chain is pulled up so that the next acid group is down, and you repeat that. And in the case of polyester synthesis, you can get very high molecular weight. And I always find that amazing because you get high molecular weight. This, what I just showed you, is inside a globular protein, which is already big. The active site is hidden inside this globular thing. And this globular thing is in such a bead. So there should be diffusion limitation. The polymer chain should actually not even fit into the active site of the enzyme, but it works. And very often people ask, yeah, are you sure it's the enzyme? Yes, we are sure because we do a lot of Planck experiments. So we do the same experiment without the enzyme, with just the acyryl beads. We cook the novozyme 435 in an oil bath so that we know that the enzyme is dead. And then you get no polymers. So it's really the enzymatic activity, but it's very amazing that that works, because there are a lot of limitations why you think it should not work, but it works. So the important thing in this whole synthesis is that the acid reacts with the serine, and we call this an acyl enzyme intermediate. And the natural action that's also happening in our body when we digest the fat with water, it's in hydrolysis. With hydrogen peroxide, you can form peracids. With alcohols, you can form ester bonds, and with amines, you can form amide bonds. And this is something we reported for the first time to make polyamides with enzymatic synthesis. So we started with not the lactones. So with the lactones, you make a polyester, and we started with lactams to make polyamides. And we started with the smallest possible ring, the ring-closed beta-alanine, or it's in organic chemistry, it's called 2-acetyl, also in polymer chemistry, it's called like that, of course. So you see it's the ring-closed beta-alanine, and the polymer would be poly-beta-alanine. And yeah, we just tried immobilized Cal-B and toluene, and you really see it works. It's the NMR spectrum of the educt and of the product, and yeah, it goes to very high conversion. But the big problem with polyamides, of course, is their bad solubility in anything, and the things that solubilize polyamides, or at least a bit. For instance, NMP with lithium chloride, no enzyme would survive that, because in principle the enzyme is of course also a polyamide. It's a polyamide of amino acids. So all our polyamide approaches, they end up with oligomers. So this is our really first approach. So you see also very low molecular weights, just oligomers. We found ways how to make this a bit higher with for instance, supercritical CO2 ionic liquids, so smart solvents, and in that case also green. But we also found out that it's not so important, because we can always polymerize these oligomers in a solid state post condensation, for instance, straight in the extruder and then spin fibers. But let's say here the highest degree of polymerizations would be 19. And if you zoom in one of these peaks of this multitoph, you also see it's a classical polycondensation, because you see linear chains and also the rings. But we found a lot of nice ways also to remove the rings. Let's say for industry that would be important, and also if we put them later in the extruder to do the post condensation, the rings would hurt our process. But there are many easy ways to remove the rings, and it works very well. And yeah, we worked a lot with this reaction, but I don't want to show you all the results. It's also a bit older already, but this was our first approach to polyamide synthesis. And then we really played a lot with this synthesis. So for instance, with aliphatic oligoamides, we varied the lengths. If you have a diacid, maybe something to mention, we always start with milligram approach. So our first polymerization, if we have a new system, we try to polymerize milligrams, because these monomers are expensive. By now we get the enzymes for free, but if you really buy a commercial enzyme and you're new to the field, it's also quite expensive. And then we actually do the polymerization in these Eppendorf shakers. You all know these little Eppendorf vials, and there are also shakers which are temperature stabilized. And then we don't work with vacuum, and that's why very often we start with an ester group, because as you know, it's easier to remove the methanol or ethanol than the water. But you can also do all this polymerization with the diacids, and it's of course greener because it's more atom efficient. But here you see we screened various aliphatic diamines, and we also use different enzymes. Cutinase is also a hydrolase, and we do different immobilizations of the cutinase and the acarel bead immobilized novozyme 435. And then we do one-step and two-step polycondensations, and then we get different results. We also get different microstructure. We also get different end groups. Again, I was saying in the beginning that it's nice to start in this field, because there's really a lot to find out still. if you're interested in synthesis, that's really something that you can hardly have with, for instance, free radical polymerization, because you can also have a lot of detailed information, of course, but here about microstructure, about end groups, it's a bit in between biochemistry and polymer chemistry. So for me, it's still amazing what you can do in this field. And here you see what I already told you. You can get not very high molecular weight, so you have to do a post condensation. And we can actually explain in this table as long as there is also, of course, already a finished PhD thesis. We have a lot of different enzymes. We have a lot of different immobilizations. Then we very often not just have one step and two step. We also have azeotropic polycondensation and everything you can find in the textbook. And then it's a big puzzle to explain these different results. But by now we can actually explain them, because we and also others also came because of these many experiments we did. There's a lot you can explain, and we can also steer these directions to certain end groups, but also to different microstructures. And when we started with aromatic or semi-aromatic structures, in the beginning, I thought this will not work, because usually enzymes don't accept such structures. But actually, these extremophiles like Calbi, they really don't care. So if you have an aromatic diamine and an aliphatic diacid, it really works very well. And I already told you that we are always looking for the end groups, and of course, the molecular weight and dispersities. And you really see that you have a very low molecular weight, but this one already has a melting point of 230 degrees Celsius. And so you're coming into the range of high performance polymers already with a degree of polymerization max, so the average is a lot lower. And then if you do a post condensation, these are high performance polymers, and you do the pre-polymers in a green enzymatic way. And the same if you have the aromatic diacid and the aliphatic diamine. It also works very well here. The degree of polymerization, the maximum is even lower, but you again have very high melting points. So even aromatic structures work, and you get very interesting polymers. And one thing I wanted still to show you before I switch to the furan-based polymers is another textbook example why enzymatic polymerization is interesting. It's the polymerization of itaconic acid or itaconic acid esters. And for those of you who have worked with this monomer before, if you want to do the polyester from this monomer, and you do a melt polycondensation, the temperatures are too high, and then radicals will always be formed, and then you have a radical reaction on this double bond, and you have automatic cross-linking. If we do it with our enzymatic polymerization, we do it at lower temperatures. We have this free double bond, and we cross-link it later if we want. And this is, for instance, also interesting for 3D printing approaches. It's a bio-based polymer, it's a green synthesis route, and you can later cross-link on demand, which you can before not if you have this, if you have a classical melt polycondensation. And here again, what I already showed you, we can play with the way we do the polymerization. If you do 2-stage in bulk, it's different than 1-stage in bulk, which is not even in the slide. But if you do a azeotropic polycondensation, you get higher molecular weights. And we can also tune, which is difficult with melt polycondensation. If you have different feed ratios of itaconate or itaconic acid, you can really steer how much itaconic acid is later in the polymer. And also here, this was the first time we actually studied all the different ways how to do the enzymatic polymer condensation, with what microstructures do we get and what end groups do we get? And it's really extremely interesting to look into that, and it's also a bit like when I teach polymer chemistry, I try to teach about polycondensation, and so many of these really basic things come back here, which is nice, because also when I teach it, I try to tell the students, it's important, because also it's important for the polyester that you wear in your clothing. And here again, you see how important it is to really understand this this actually very basic reaction mechanism. And here very often we also vary the lengths of the aliphatic chains, and you see that adipic acid or the adipate works the best. And this of course comes from the enzymes are used to a certain chain length, and that is most of the time dependent on which fat they are used to. So most of these natural lipases, they prefer longer aliphatic diacids and diols, because that's also what the fat is that they are used to, because the triglycerides don't have short chains. But I wanted to tell you about furan-based polymers, and yeah, so I now come to this. And the reason for furan-based polymers is the replacement of terephthalic acid-based polymers, of course. And we use a lot of this plastic because we all have these plastic bottles that we drink of. And I think you all know these numbers from the Ellen MacArthur Foundation from 2016, that if we don't stop what we are doing right now, this I find the most disturbing one. The others are disturbing as well, but if you don't stop, then in 2050 we have one fish per one plastic bottle by weight in the ocean, and that's of course not what we want. So we have to do something. So one is the bio-based approach to replace terephthalic acid by furan-based monomers. And one that's commercialized, that's polyethylene furanate, PEF. It's a biomass-derived FTCA. I come back to that later, but this polymerization has a problem. If you do a melt polycondensation, it forms furfural because it's furan-based monomer, and it leads to discoloration. So this is something that in the whole furan-based monomers, if you have the temperature too high, it gets darkish brown. And this is again where we don't have the problem, because we have to do our enzymatic polymerizations at lower temperatures. And I want to show you what we did in this field by enzymatic polymerization, and why I think this improves the sustainability. So the monomers that we use is the furan-based diol and the furan-based diacid. And I'm pretty sure you hear a lot about FTCA, because this is the monomer also of PEF. And a lot of people polymerize FTCA. Now this diol is not very stable, and because of this, the position of the two hydroxy groups, it's not very stable in melt polycondensations. That's why you find hardly any reports of BHMF-based polyesters or polyamides. And then again, with enzymes, you have no problem with that, and we synthesize a lot of BHMF-based polyesters and polyamides. And it's a very good monomer, so it should not be left out. So you should not just focus on FTCA. So I really hope this is again like a stimulus for enzymatic polymerizations. You can get both monomers by a reduction or oxidation of HMF, which is coming from biomass. I should change this picture. It's really non-edible biomass. It's really waste, and you make HMF. And the oxidation and reduction leads you to the monomers. And this can also be done enzymatic or fermentative. This is done by my colleague here in Groningen and Marco Freyer. The big problem at the moment for industry is still that this coming from the carbohydrates to the HMF leads to a lot of side products. So they are still working on making this reaction more efficient. This oxidation and reduction is actually quite under control in the industry. But here they still lose a lot of material, and this is in terms of green chemistry, atom efficiency, not yet completely under control. And why are we doing that? Because we want to replace terephthalic acid-based polymers like PET with something bio-based, FDCA-based polymers, and for plastic bottles, but also for more high-tech gear. And this is a picture I stole from Avantium. This is with NatureWorks, the two biggest producers of PEF. And Avantium is a Dutch company in Amsterdam, and they are a spin-off in principle of DSM. And what they found out, but also others in the field, of course, is that the polymer has a bit higher thermal stability than PET. It's still not that you can really have coffee cups from PEF, but there are, of course, again, ways to do that. It's bio-based. Because it has a higher gas barrier properties, so you can make the plastic bottles thinner. And that's, of course, something which really plays into sustainability, because if your plastic bottle weighs less, and then the 1,000 plastic bottles that get transported need less gas, so this is really good. It's 100% recyclable, but of course PET is also 100% recyclable. Yeah, this gas barrier properties are really better. And you might have seen these commercials from Coca-Cola, the plant-based bottles, but there is at the moment not a single plastic bottle out there which is pure PEF, because the production capacity in the whole world is not very high. And they all have problems with this yellow discoloration and decarboxylation in the polycondensation because of the too high temperatures for this monomer, and the diol they cannot even handle. So we started with furan-based polyesters, polyamides, copolyesters, and polyester amides. And you see we did different things in this polymer classes, and I want to show you a few of them. So in principle, what you do, you have the HMF or the FDCA, and you co-feed it a flexible counterpart. And then you have the FDCA-based polyester or BHMF-based polyesters. And we also already did a lot in this field. So of course you cannot just do PEF, but also a lot of others. I already told you that it's very difficult by normal melt polycondensation to polymerize this. But for the enzyme, it really doesn't matter, because you don't have too high temperatures. So we could report a lot of BHMF-based polyesters, but also a lot of FDCA-based polyesters. And we also did polyamides, which also works very well. And so we are still also busy with that, because this is a big playground. And for instance, if you just have Calbi, so a commercial known enzyme, it takes a lot of FDCA and a lot of flexible diols. But for instance, if you would like to do a FDCA isosorbide polyester, it doesn't work properly. It's too bulky for the active side. And then again, it's interesting that you can change the enzyme, and then it might work, because if you have an enzyme which is a wider open active site, then you can do this polymerization. So there's a lot again to do in this field. And if you look in this polymerization, and it's really just the monomers, the enzyme, and then you let it run like a classical polycondensation. So there's not a trick in this whole thing. But we by now also learned that with the higher reaction times, we get higher molecular weights. And if the diol chain length gets higher, we get higher molecular weights. And but at a certain point, it also goes down again. And we have a lot of ways how to tune this polymerization. And we also know a lot about this polyamides. And here again, I can show you that in the polyamide case, there's an underlying chemical reaction, because polyamides are faster to be synthesized than polyesters, but it's really catalyzed by the enzyme, and it's not just appearing and the enzyme is there. And again, also here we screened different diamine lengths, and you see again that the enzyme prefers a diamine with the length of 8 carbons in the chain, and this is again sort of the natural length that it's used to from the fat in nature. And yeah, you see again, we don't get the highest molecular weights because of solubility issues, but it's in principle a reaction that we have under control, and that where we can do a post condensation. Yeah, and this odor preference comes from the natural selectivity of the enzyme. And we know that comes from H.N. Jenger, from work also from the 90s, that these enzymes like heteroatom polyamides, so you can also use them as diamides. And there you also see that it's that this also works in our case. The question is if these polymers are valuable at the end. Because we also know that they are thermally not that stable than if there would not be this heteroatom and the diamine. And so we synthesized a lot of polymers, and we also always check the thermal and the mechanical properties, of course. And we found that there are maybe some polymers which might even be better than PEF, where the processing window is even wider open and which have a higher thermal stability. But of course, they were replacing PET by PEF because it looks the same. But I think there would be other polymers which might be even better to introduce them to industry to replace PET than PEF. And one thing which amazed us in the beginning, that in these reactions we sometimes even get higher molecular weights than the normal melt polycondensation. Because what people always complain about is that, and which is in most cases also true, I have to confess, that we get lower molecular weights than a normal melt polycondensation. But if you, for instance, look at this PDF polymer, then yeah, we get higher molecular weights. And if you compare the properties of the comparable polymers, they are more or less the same. So you can really replace this oil-based polymer with a bio-based polymer, where I also have to say, by now they already make terephthalic acid also bio-based. And also the polyamides are comparable, but there are also no terephthalic acid-based polyamides used for anything. So here you would actually replace something which is not used. So it's nice from an academic point of view, but we have nothing to replace. So if you talk about I want to replace something for future sustainability, yeah, then this is senseless because you're not replacing anything, but it's still very interesting research. And this is our holy grail, and we are not there yet. So we would actually really like to polymerize FDCA with BHMF, get this structure, and maybe also the polyamide. But this is really too bulky for all the enzymes we have yet. So you see, you get very low molecular weights. But Dina Mania, who was working on that, was developing different strategy for that. So she was co-feeding this polymer. So we would actually like to polymerize this with this. Doesn't work. So she was co-feeding it a flexible diol or a flexible diacid, and then it really works. So we get high amounts of this structure. So we would actually like to have this structure, but here you get a high amount of this and a bit of this, and then it works. And so we are approaching it somehow from the bottom. And this was actually really nice. So you see in the IR and the NMR that you really have, that you can quantify that this structure that we want to have, and yeah, you can also increase it. And we also found that the different strategies have a different success, and this really comes from the fact that I showed you in the beginning, this mechanism. So you first go with the acid group down, and if this is an FDCA and you release it with something flexible, that works quite well. So this is strategy 1. But if your acid group is first a flexible one and then you release it with something bulky, that's not so attractive for the enzyme. And that's why the first approach gives you the higher degrees of polymerizations. Yeah, and if you really put too much FDCA or also HMF in there, the enzyme really goes on strike. So it's really the active site has a certain dimension, and not everything fits in there. And I think here we should also look again into enzyme design. And this is what I already told you. Important is that first the acyl enzyme intermediate is formed. And then if it's released by something flexible, it's easier than if it's released by something more bulky. But these polymers are already now, with the high amount of aromatic, quite good thermal behavior. You see good melting temperatures for again, for high performance polymers. They are very well processable. Mechanical properties are also good. They are also thermally stable and semi-crystalline. And really the last thing I want to show you are the polyester amides that we recently synthesized. So of course you can have the FDCA and co-feed it a flexible diol or diamine, or you co-feed it in hydroxyamine. And yeah, we did both, and we look in 1-step, 2-step bulk solution. We always do that, and again we see dependence on different methylene unit chain lengths. But the reason why I wanted to show you that, and I don't want to go into detail, is that we actually do that in ionic liquids, and that's not on this slide. But the different solvents, and so this is one of the first approaches where we went to ionic liquids and green solvents, because it's difficult to work in bulk, and toluene you want to, of course, you want to avoid. We still get lower molecular weights. We also started to work with deep eutectic solvents, and then the story is again different. I don't have results on that, but we also see that, for instance, with the ionic liquids, we get discoloration, which is of course not nice. So this is not the discoloration of the monomer, but this really stays in there from the ionic liquid. So this is interesting, and I think we should move more and more into this green solvents. But yeah, this is for us really work in progress, but this is something we are getting really interested in that. And I hope I had convinced you that it's really interesting to work with these furan-based polymers, and also that enzymatic approaches really have are actually superior to this classical melt polycondensation. And with this, I want to end my talk. Before the summer, we had our 55th party. Our department was founded 55 years ago. So here you also see the founding father of our department, Professor Katja. He's by now over 90. He always comes to these reunions. And of course, I want to thank my group. So Dina Mania was doing most of the work that I showed you, and Fitri is at the moment finishing her PhD thesis also on this topic. Of course, I want to thank all the organizations that fund our research. And I have 2 more slides, so I would like to remind you, or if you have not heard of that yet, inform you that journal Polymer has for European authors the Andrew Keller Award. So if you are considering to submit your next paper to Polymer, then please also nominate yourself or one of your co-authors, for instance, your PhD student, for this Andrew Keller Award. And we will select at the end of the year for this very nice award. It's always nice to win an award. And the last slide I want to show you, you might have heard that in 2025 the European Polymer Congress comes to Groningen, and it's 22 to 26. And if you have time, I hope it's still time in your agenda. I would love you to come to Groningen. And with this, I would like to thank the organizers again for organizing that, and you all for listening. And I hope I can answer some of your questions. Thanks a lot.